Swayam Prabha. Digital India. Educated India.
So at any point we know what is minus grad f. F is equal to x minus 3 the whole square plus y minus 3 the whole square. H is equal to x plus y minus 1. At the optimum point, necessary condition is that minus grad f is equal to lambda times grad h, where lambda is some undetermined scalar. Now if you ask me how I will determine it, we will see there is enough information for me to determine both the optimal point and this scalar lambda over here. Now what is grad f? Grad f is equal to 2 into x minus 3, and the second component is 2 into y minus 3. Now grad h is equal to 1 1. Now I know that this is equal to lambda times 1 1. Right. So for an optimum point, minus grad f should be equal to lambda times the gradient of the constraint. Now how many unknowns are there? 3 unknowns. X is an unknown, y is an unknown, lambda is also an unknown. So I have only 2 equations. So what do I need one more equation. Where is that going to come from? The constraint. Remember, the constraint always has to be satisfied. I cannot choose x and y arbitrarily. X and y has to satisfy the constraint x plus y minus 1 equal to 0. So there are 3 equations, 3 variables. And in this case they happen to be linear, so I can use any technique. You can use any technique to solve linear equations and you can find the solution in this case. It also automatically gives me the scalar over a lambda. This scalar is going to be called Lagrange multiplier. Lambda is called the Lagrange multiplier. Now when there are equality constraints, I don't want you to think that lambda should have a specific sign. When there are equality constraints, lambda can be positive or negative, or even 0 in certain cases. There is no specific or any special sign for lambda. Lambda can be positive, negative or 0. There is no specific sign for lambda, because if you recall what we did, we said only minus grad f and grad h should be collinear. I did not say that they should be pointing along the same direction, because the reason is this: h is equal to x plus y minus 1 is equal to 0. You could formulate a problem which says no, h, I won't write this as x plus y minus 1 equal to 0. For whatever reason, you might write it as 1 minus x minus y equal to 0. And for this, grad h is now pointing in the other direction. So for this also, however, geometry the same condition has to satisfy. Minus grad f, let me call this h prime, minus grad f is equal to lambda times grad h prime. But grad h is going to point, h prime is going to point in the other direction for this constraint. But the constraint is really the same. Only thing that has changed is my representation of that constraint. In one case I wrote it as x plus y minus 1 equal to 0. Now I am writing it as 1 minus x minus y equal to 0. Both of them are the same. There is really no difference. In both cases, minus grad f and grad h should be collinear. That's all I can claim. Or they should be parallel. In which case they are just related by a scalar multiple. And therefore in one case if lambda is positive, in the other case lambda becomes negative, because grad h is pointing in the other direction. So lambda cannot have a specific, there is no specific sign for the value of lambda over here. You can flip the entire table around by using the negative value of the constraint and get gradients of the constraints pointing in the opposite directions. The signs of lambda will change. So lambda has no preferred sign when you are dealing with equality constraints. And I want you to keep this in mind when we do inequality constraints. When we do inequality constraints, however, lambdas have a special sign. And why is that? We will see that in the next illustration. Now this is, I chose a very easy form of a quadratic function and a linear, and a constraint was a linear. You can generalize these to arbitrary functions, arbitrary nonlinear constraints. We will also be able to generalize this to arbitrary numbers of constraints, arbitrary vectors and higher dimensions. I will not be able to give you, unfortunately, geometric interpretations like these, because I am constrained to drawing things on the screen over here. I am only constrained to giving you 2-dimensional illustrations, and therefore I can only work with some examples of this kind. For higher dimensions, I will be able to only write down the constraints, and we will have to use our intuition. We will not have time to prove it, we will have to use our intuition and accept those as a generalization of these geometric intuitions that I gave you here. Now we will look at inequality constraints. Now the problem is going to be slightly different over here, where I am going to say I want to minimize x minus 3 the whole square plus y minus 3 the whole square such that x plus y is less than or equal to 1. In the previous case it was x plus y equal to 1. Now I am saying x plus y could be equal to 1 or could be strictly smaller than 1. So what does that mean over here? So this is the line x plus y equal to 1. In the previous case, when it was an equality constraint, I had to be on this line. I could not go out of the line. Now I have some more flexibility. I can go anywhere over here also. I can be on the line or I can go into this side. I can go away from the line, but I cannot go in the other direction. These directions are not allowed, because if I go in this direction, x plus y will become greater than 1. If I go below the so-called below the line, x plus y will be strictly less than 1, and those I am allowed to go. I can be either on this line or I can go below the line. So let me clean this up. So I'll just ask you to keep in mind, maybe over here I will use this as an arrow to show that these are my feasible directions. I can be on this line or I can go into this feasible region. Now again I'll use the same, this is my point over here. I'm asking the same question, which I can be not necessarily on this line. This line divides the space into two what's called half spaces. One is on this side above the so-called above the line, and the other is called below the line. So what I'm now asking is, what is the shortest distance of this half space from this line, from this point? And in this case again geometrically, could this be a point? Can this be an optimal point? Can a point in the interior of the feasible region, or which is away from the line? This is clearly not an optimal point at all, because it is not even feasible. So I will not even worry about points on the other side of the line. I will only worry about points which are below, on the line or below the line. I only have to look at those points and ask the question, is it a feasible point or not? Again, we know geometrically, because it cannot be a point which is below the line, it has to be a point on the line. So it looks like we arrived at the same case as the last case. It has to be some point on this line over here. Over here we know that it cannot be, I hope all of you agree that it cannot be a point which is strictly below the line, because if it is below the line, I can go closer to the line and my distance of the point from this point 3, 3 will only decrease. So it cannot be a point which is strictly below the line. It has to be a point somewhere on the line. That much is clear. Now if it has to be a point somewhere on the line, we can use the same arguments that we did in the equality constraint optimization case, and then make the same argument that it has to be the point where the perpendicular intersects the line has to be the optimal point. Now however, the same argument I will use, minus grad f should be equal to at this point now. Okay, I'll use the same argument. Now what is going to be perpendicular and so on? Let me ask this, let me look at those questions. Now if I am at this point, remember in the previous case I said there were, let me draw it over here just to make it clearer. If I am at this point, which are my feasible directions in which I can go? I can go along this direction, I can go along this direction, but that is not the only direction in which I can go. There are many other directions also which I am allowed to go. I can go along these directions, I can go along these directions, I can go along these directions, but I am definitely not allowed to go along this direction because it takes me on the other side of the line. So this I will rule out. I will not be able to go on the other side of the line, but I can be on the line or I can go in below the line. Those are all my feasible directions. So unlike in the equality constraint case where there was only two directions which I was allowed to go, basically along the line, in the inequality case there are several directions in which I can go. I can go along the line or I can go into the interior of the half space or below the line. All these directions I am allowed to go. Now in this case, what are all my feasible directions? My feasible directions are all those which make an obtuse angle with grad h. My grad h is also pointing in this direction, because if you look at grad h is equal to 1 comma 1, and you can see that grad h is also pointing over here, and minus grad f is also pointing along this direction. So in this case, however, you can now, by using the same geometric argument, I will be able to write minus grad f equal to lambda times grad h, because grad h is pointing along this direction, minus grad f is pointing along this direction, and they are not just parallel, but in this case you can see that minus grad f is pointing in the same direction as grad h. So what can you say about the sign of lambda? Lambda has to be, it cannot be negative, because in this case, as you can appreciate, minus grad f is pointing towards 3 comma 3, grad h is also pointing in the same direction. It is not just collinear, but I will now make an argument that lambda should have a sign. The sign of lambda is important. In the previous case, I argued that the sign of lambda was not important because I could flip the sign of h and grad h direction also flipped, therefore the sign of lambda could change. But in this case, in inequality constraints, I cannot make the same argument. Lambda, whatever sign it has over here, that is important. In this case, lambda was greater than or equal to 0 because minus grad f and grad h are pointing in the same direction. So this scalar has to be positive. Now you can make the same argument that I did in the previous few minutes and say, no, why can't I not flip the sign of grad h? That I cannot do, because if I flip the sign of grad h, my constraint surface, my constraint itself changes. In the previous case, my constraint was an equality constraint. So it was x plus y equal to 1. So grad h, whether it points here or here, it is the same. However, in the case of inequality constraints, my grad h has I cannot flip the direction of grad h, because h has to be less than or equal to 0. So my h is x plus y minus 1, this has to be less than or equal to 0. So if I flip the sign of h and say this is, if I make h negative, then it gives me a totally different region, it gives me totally different problem. I will go in the other direction. H has to be less than or equal to 0, h cannot become positive, because my constraint is written as x plus y minus 1 less than or equal to 0. So the sign of h is important over here, therefore the sign of grad h is, direction of grad h is also important. I cannot flip the direction of grad h. So here you will, if you are with me until here, you will appreciate that minus grad f and grad h have to be collinear with each other. Not just collinear, they have to point in the same direction, therefore the multiplier, the Lagrange multiplier lambda has to be non-negative. Okay, now I will go to a case, now I will do another inequality constraint problem. So it is very similar to the previous problem, except now if you observe carefully, I have changed the sign of the inequality constraint. It is not x plus y less than or equal to 1, it is really x plus y greater than or equal to 1. So my feasible region is not, this is my line x plus y equal to 1, my feasible region is not the space below the line, it is really the space above the line. So now what is my optimum point? I can be anywhere over here. I can be anywhere over here, right? So now I can be on the line or above the line. Now does it make, in the previous case we could argue that I had to be on the line. Now in fact I will make the other argument, I cannot be on the line, because if I am on the line, I can go closer to the point 3 comma 3 and reduce my value of the objective function, or I can make my distance smaller. So in fact I cannot be on the line. So which point is the closest from this 3 comma 3 now? And my feasible region is all the space above the line. Which is my closest point? 3 comma 3 itself. My optimum is 3 comma 3. Right? That we know. The closest point of 3 comma 3 is 3 comma 3 itself, and that is a feasible point. In the previous case, 3 comma 3 was not a feasible point because I had to be below the line x plus y equal to 1. In this case, I can be above the line x plus y greater than or equal to 1, and it satisfies this constraint. And we can see that 1 minus 3 is equal to minus 5, which is strictly less than 0, so it satisfies the constraint. In the previous case, the constraint was x plus y less than or equal to 1, therefore 3 plus 3 was equal to 5, which was greater than 1, and that was not a feasible point. In this case, it is a valid feasible point, and therefore my optimum point is indeed 3, 3. Now, what is the geometric condition that is happening over here? In the previous case, we could argue that the gradients of the objective function and gradients of the constraint should be collinear. In this case, what is the geometric constraint in terms of gradients? What constraint can I write? At the point 3, 3, what is equal to, there are obviously grad f and grad h are not pointing in the same direction, because at this point, what do we know about grad f? At the point 3, 3, grad f is 2 into x minus 3, 2 into y minus 3, and this is equal to 0, 0. At the point 3, 3, the gradient is equal to 0. So in the previous case, in the case of the equality constraint, minus grad f was collinear with grad h. In the case of the inequality constraint, minus grad f was along the same direction as grad h. In this case, third case that I have given you, it turns out that minus grad f is equal to 0. So now we'll forget about equality constraints. Now I am just going to come up with a way of generalizing whatever we know about inequality constraints. Then we will generalize whatever we know about equality constraints and come up with one set of conditions. So what are the two possibilities that we have over here? So if I have minimize f of x subject to, let me write down what all things we know. Suppose I have a constraint g of x equal to 0. For an optimum, this is an equality constraint problem. So I know that minus grad f should be equal to grad g, and g of x should be equal to 0. I have to solve all of these equations together if it is an equality constraint problem. Now if it is an inequality constraint problem, let me write it in this form: minimize f of x subject to h of x less than or equal to 0. I have two cases. At an optimum point, either h of x is strictly less than 0 or h of x is equal to 0. H of x is equal to 0 is the case where the inequality constraint problem, the optimal solution lay on the line. At that case, what do we know about the optimality conditions? Minus grad f is equal to lambda times grad h. Let me just go back and make one. I want to keep certain constraints, conventions over here. When in inequality constraint, let me recap, there is a minimize f of x subject to g of x equal to 0, a single equality constraint, x could be in whatever dimension. Using the same ideas, I will argue that minus grad f should be collinear with grad g, and the sign of lambda over here can be positive, negative, or in fact even equal to 0 under certain conditions. Because g of x is equal to 0 is the same as minus g equal to 0, so the directions of gradients of equality constraints can be changed, and you will not be stuck to the preferred sign of lambda. Now in the case of inequality constraint problem, when I have minimized f of x subject to h of x less than or equal to 0, there are two possibilities. What are the two possibilities? At optimum, either h is equal to 0 or h is strictly less than 0. Let us do the case when h is equal to 0 first, then minus grad f should be equal to mu times grad h. We know this, and we also know that mu has to be greater than or equal to 0. The sign of mu is important. Sign of mu cannot be negative, mu has to be non-negative. And what else do we know? H is equal to 0. So we have these conditions of optimality when the constraint h is when h is what is called active, or when h is equal to 0, these conditions have to be satisfied. On the other hand, when h is less than 0, that means there is no constraint which is binding you, right? That is, you are in the strict interior of the feasible region, so you are allowed to move. If you take very small displacements, you are allowed to move in any direction that you can. Therefore, the necessary condition of optimality is grad f is equal to 0. Exactly what we saw when we are allowed to be on the other side of the line, when we said we want to minimize the objective function subject to being above the line x plus y greater than 1, we saw that gradient was equal to 0. Now, I don't want to ask, suppose I ask me, can you concisely express these conditions? That we'll worry about equality constraints later, we'll come to that later. Can you concisely express these constraints, conditions of optimality for inequality constraint problem? Don't give me a decision tree. This looks like a tree, right? It says if h is equal to 0, do this. If h is less than 0, do this. But I don't, when you ask for conditions, I don't want to have a decision tree given to me. Can we algebraically write these constraints as concisely as possible? And it will automatically, depending on the condition, it will automatically go to one of these branches of the tree over here. And the way I do that is, I will write minus grad f is equal to mu times grad h. This has to be satisfied, but in this case, it is not. It is satisfied in the case of the left hand side when h is equal to 0, but in the case when h is less than 0, minus grad f is not equal to mu times grad h. So what can I write over there? I will put one condition over here, h of x, mu times h of x is equal to 0. And I will write the condition mu greater than or equal to 0. This is called the mu times h of x equal to 0 is called the complementarity condition, because when the product of two numbers is equal to 0, it forces at least one of them equal to 0. So let us see what happens over here. When h is strictly smaller than 0, this condition mu times h equal to 0, what does it force? It forces over here mu times h is equal to 0 over here. When you have h is strictly less than 0, because of the complementarity condition mu times h equal to 0, it forces mu to be equal to 0. And when h is equal to 0, we don't care. I mean, mu is already on the other side, other arm of the decision tree. When h is equal to 0, mu h is equal to 0, so you don't care. So in both cases, however, in the case when h is less than 0, because mu is forced to be equal to 0, minus grad f becomes equal to 0. And when h is equal to 0, you have minus grad f equal to mu times grad h, and mu has to be the last condition over here, the non-negativity condition forces the correct alignment of the directions of minus grad f and grad h. So they should be aligned in the correct directions. If the constraint is exactly satisfied as an equality, this is called an act. This means that this constraint is active. For active inequality constraints, the Lagrange multiplier will force the gradients to act along certain directions. When the constraint is inactive, the Lagrange multiplier correspondingly will be equal to 0. For inequality constraint optimization problems. For equality constraint optimization problems, minus grad f is anyway equal to lambda times grad g. And lambda for inequality constraint problems can be positive, negative or 0, there is no condition. For inequality constraint optimization problems, the Lagrange multipliers have to be non-negative, and in addition, the complementarity condition has to be satisfied, which means at least one of the two conditions has to be satisfied. Either the Lagrange multiplier is equal to 0 or the constraint is active. Either if h is strictly less than 0, then mu is forced to be equal to 0. In which case, that particular constraint is not preventing you from going anywhere and improving the value of the objective function. So this is the idea of inequality constraint optimization problems. And equality constraint optimization problems, the gradients of the objective function and the constraint gradients have to be collinear.